Nowadays, data is often distributed and owned by different participants. There is an emerging need to provide a joint visualization, such as a TSNE projection, to serve as the full picture in data analysis. If the participants are privacy sensitive, how can we build a joint projection without data leakage? Conventional embedding algorithms, such as the TSNE, are designed for single-site computation and require data centralization. Privacy leakage may happen in 3 stages in the visualization pipeline.
Firstly, we extract contours of virions and distribution of spike proteins. From a newly estimated contour, a 3D mesh with evaluated triangles is obtained. In the last step, rules describing relations between protein instances are defined by the user. The resulting model is created by application of all rules on the generated 3D mesh.
Hello and welcome everyone to this full paper session on finance and blockchain. This is one of the last paper sessions of this year's VIS 2020. And we have 5 interesting talks ahead of us. And as you know, please post your questions as they come on Discord or the YouTube channel. So we'll start right away with the first talk on TaxThemis, interactive mining and exploration of suspicious tax evasion group.
Hi everyone, I'm Yating Lin, a graduate student at Xi'an University. Today I'm going to present TaxThemis, an interactive system for exploring suspicious tax evasion groups. Before we begin, let's go through some relevant background knowledge. Tax evasion is a financial crime against the tax system in which taxpayers deliberately report false financial positions to deny their tax obligations. It has become a severe economic problem for many countries. For example, this map shows how much tax revenue was lost in a year due to tax evasion for different regions. These figures could have been part of the government budgets to improve people's quality of life. Our work aims to detect a specific tax evasion behavior that is conducted by some associated taxpayers. We call it RPTTE. It has 3 characteristics. First, the taxpayers should have a common beneficial owner. That means they have a common interest, and they can benefit from a reduced overall tax burden. Such taxpayers are also known as related parties. Second, they must conduct transactions to establish a channel for RPTTE. Third, taxpayers who carry the transactions should have different tax obligations, such as a profit status difference. For example, here we can see that a taxpayer at a profit transfers some earnings to a related party at a loss. In the beneficial owner's perspective, the 2 companies' overall profits have not changed, but he can pay fewer taxes. The existing inspection methods can mainly be grouped into 2 categories, machine learning and network-based methods. The machine learning method mainly focuses on creating models to automatically learn the underlying features and calculate each taxpayer's suspicion scores. Another approach is to classify taxpayers into tax evaders and non-tax evaders. However, these methods have limited practical values because of their black box nature. The features are not explainable to tax inspectors. Also, the models are highly reliant on training data. On the other hand, the network-based method detects tax evasion groups by matching some expert summarized patterns. Although it makes sense to tax inspectors and is able to find all suspicious groups, the problem is twofold. First, the patterns that describe related parties are quite prevalent in reality, resulting in a high false positive rate. Second, the methods cannot provide useful evidence for tax inspectors to verify the suspicious groups. To address the challenges, we propose TaxThemis to help tax inspectors explore and identify suspicious tax evasion groups. Our work combines visual analytics with the network-based method to provide context and support interactions for filtering the result set. It integrates the domain knowledge of tax officers with the computational power of machine and the expressiveness of visual analytics. TaxThemis has 3 models, namely data preprocessing, data analysis, and visual analysis. First, the raw tax-related data is preprocessed with the data masking techniques and then constructs into a taxpayer network and a trade network. Then, the data analysis model fuses the 2 networks to support automatic suspicious RPTTE group detection. It also extracts features from each group for ranking and further analysis. Finally, the visual analysis model supports interactive exploration through full coordinated views, which is a post-processing analysis of the suspicious groups and their context. The control panel consists of a bar chart to set the preferred period. It offers a temporal summary of the daily related party transaction amount. It reveals a cyclic pattern where most of the peaks are near the end of the month. We suspect that this is because the profit manipulation should happen after tax evaders know how much taxable income they have. There is also a parameter selector to support network fusion. The parameters determine the size and the relevance of suspicious RPTT groups, narrowing down the information-seeking space. The group overview shows a list of suspicious groups. Each row represents a group. This view is designed to help users focus on the most suspicious group. The arc diagram-based glyph visualizes the topology of the related party transactions. Users can evaluate the complexity of the underlying trading relationship and estimate how much effort is required to investigate the group. The bar chart shows three group features that correspond to significance, historical performance, and suspicion. Users can rank by different features to find groups of interest. The graph view shows the hierarchical investment relationship and the related party transactions within a selected suspicious group. We use the diagram layout to reduce cross-links. In most cases, it gives the graph more structure and clarity. Each circle represents a taxpayer. Its border color encodes the entity type, and its fill color encodes the period and profit status. Taxpayer with tax evasion records are marked by drawing an exclamation point in the circle. Each link represents a relationship where its border color encodes the investment or transaction type. When we hover a transaction, the corresponding investment relationships will be highlighted to help users find the common beneficial owners. This view is designed to help users locate a suspicious transaction quickly and demand more details. After selecting the transaction in the previous view, the detail view will visualize the two traders' continuous profit status using two calendar heat maps. The background color of each rectangle encodes the cumulative daily profit of a taxpayer. The scatters on the heat map represent the transaction, with the amount encoded by size and the cash flow encoded by colors. The arrows also indicate the cash flow direction. The redundant design provides more intuitive perception to users. Here, we would like to demonstrate how TaxThemis works with a real example. Let's look at the first quarter in 2014 and use the default parameters to run the network fusion algorithm. The algorithm will return a collection of suspicious RPTTE groups and show them in the graph overview. We can notice that the first suspicious RPTTE group is very complicated from the glyph. For demonstration purposes, let's choose the second group instead. From the graph view, we can see the investment and the trading relationships between the taxpayers. The orange node is an investor, and the blue node is a taxpayer. They are connected with arrows where the oranges are investment relationships and the blues are trading relationships. We can see the highlighted common beneficial owner as well as the control chain. There is an exclamation mark in every taxpayer node. It indicates that all of them are former tax evaders. The fill color of the nodes has indicated the period and profit status of the taxpayers. We can see that a taxpayer in profit is transferring revenue to a taxpayer at a loss. Together with the fact that the group contains many former tax evaders, this has indicated a high level of suspicion. The two calendar heat maps show the cumulative daily profits of the two taxpayers. We can see that on the left-hand side, the brown dots are located in a blue heat map. It means that the transactions have inflated losses on the taxpayer who is earning a lot in the first quarter. On the other hand, the taxpayer on the right-hand side is the complete opposite. The arrows indicate the direction of the transaction. Let's see how did they do in the whole year. We can hide them when they have created zero clutter. From the overall picture, Although there are a small number of transactions in reverse order, the pattern that we have seen in the first quarter still holds, same for 2015 as well. All the viral cues and evidence suggested that this group is highly suspicious and should be further investigated. TaxThemis has straightforward viral designs and is designed to be understood easily. It is because our target users are mainly tax inspectors with accounting backgrounds. Standard chart and intuitive designs will be much easier for them to understand, which significantly enhance the usability of TaxThemis. This is particularly true when user studies are widely conducted remotely due to the difficult time we all face. We want to discuss some design lessons learned in designing the detail view. We could replace the calendar heat maps with a line chart to show more clarity and scalability on some occasions. However, there are a few drawbacks. First, since taxpayers' profit status can fluctuate massively, especially for small and medium-sized enterprises, it can create significant viral clutter with the intersecting lines. Second, due to the power difference between traders, the scale of the y-axis has to adapt accordingly. When users examine different related parties that involve the same taxpayer, they might find the same line being squeezed or stretched, creating difficulties for identification. Third, users have to combine both viral channels, y-location of the line and the color of the dots, to look for buyers in profit and sellers in a loss. This combination is less intuitive than comparing the diverging color in the calendar heat map. We believe that the shortcomings of line chart outweigh the benefits, leading to our final design choice. In conclusion, TaxThemis is an interactive visual analytics system to help tax officers identify and examine suspicious tax evasion groups. The system integrates the traditional data mining algorithm and visual analytics techniques through an interactive analysis processing pipeline. We demonstrated the effectiveness and usefulness through case studies using real-world tax data. Thanks for listening, and we welcome any questions.
Okay, thank you for this talk. We have Kamkwai Wong with us, one of the authors of the paper, and we'll be happy to answer questions that appear on the live stream here. I maybe start with one. I was especially intrigued by the cliff design that you have in the group overview that appears on the left side there. Can you do something with this cliff? Can you compare these cliffs or interact with it, or is it more to show how the different schemes look like?
Currently, in our version, we did not consider interactions in the glyph. But previously, we have think of some interactive, like and highlighted for like just putting the common beneficiary identification, which is already in the graph view, but we can sort of like move that interaction skill outwards to the glyph. However, we think that this type of technique might be too much for the overview because it is not quite what it is designed for. And basically, we want them to see the power of the flow and also the overall complexity of investigating the group rather than doing all the analytics over there, which might create a lot of overload to the performance over that.
Okay, I see. Thank you. We have a question from the chat, Marcel Warren. Was the system evaluated with real tax experts? And if so, what was the result?
The expert pretty much, because they were from accounting background, most of the time their system is not in have rich visualization. So this is the first time they came across with a solution with rich visualization elements. They like it very much. They would call it pretty and also beautiful. And they found that although this method is not previously used in the in the accounting principles, but then this analytics approach helped them to find another angle. Like originally, they would find period end indicators, such as the profits, which is calculated at the end of the month. However, we provide a continuous flow to the analysis, which is very helpful for them, especially when they are trying to find one single point of the crime.
Okay, thank you very much. In the interest of time, we will continue at this point. Thank you once more.
Thank you.
Kamkwai.
Thank you.
Okay, so we will continue with our third paper, which is on visualization of blockchain data, a systematic review. Let's roll it.
Hello everyone, my name is Natkamon Tovanich. I am presenting our TVCG paper on visualization of blockchain data, a systematic review, which I work on with Nicolas Heulot, Fekete, and Petra Isenberg. In the last 10 years, blockchain had gained more attention among both technologists and public audience. In short, blockchain is a large transactional database stored in a peer-to-peer network. Users can make a transaction to each other directly without third-party control by a bank, government, or any organization. Besides, blockchain data is encrypted with cryptography to conceal the identity of user. In this work, we present a systematic review of the current state of the art of blockchain visualization tools. First, we collect blockchain visualization sources and then propose a classification scheme to group those visualizations. In the end, we look at research opportunities and open challenges in blockchain visualization. From the data collected from both research articles and publicly available online tools, we found a total of 76 blockchain visualization sources, in which we separate them into 3 categories. There are 14 visualization articles that visualize blockchain-related data, 17 data analysis articles that use visualization to communicate the empirical analysis result of blockchain, and 45 online visualization tools developed for blockchain users. You can see that online tools are dominant in our survey because blockchain is an emerging field and visualization tools are firstly developed by the blockchain community for practical use. We accessed those visualizations in detail and came up with 5 features to classify blockchain visualization sources. 1. Target blockchain. 2. Blockchain data. 3. Target audience. 4. Task domain. And 5. Visualization type. Due to the limited time of the presentation, I will just briefly explain each classification scheme. For more detail, I would like to invite you to read our full paper. For the target blockchain, we found that most existing blockchain visualization tools display data from Bitcoin because it is the most popular and widely adopted blockchain, followed by Ethereum, another cryptocurrency that can additionally execute smart contracts. Only 13% of visualization display other kinds of blockchain, such as Litecoin, Namecoin, and Dash. Notice that all target blockchain we found were cryptocurrency blockchain. For the blockchain data, the elements of blockchain can be simplified into 3 main components. The first component is data stored in the blockchain, which includes transaction, address, and blocks. The second component is the peer-to-peer network, which store, validate, and maintain blockchain data. The data in this layer include information about nodes and mining activity. The third component is external data, such as market price, news, and social media, which affect the activity inside the blockchain network. Based on the blockchain data, we separate blockchain visualization sources into 5 task domains. The first 3 tasks, transaction detail analysis, transaction network analysis, and cybercrime detection, focus on the presentation of data stored in the blockchain. On the peer-to-peer network layer, the peer-to-peer network analysis task domain gives an overview of activity in the blockchain network. Some cyber attacks in blockchain also happen at this level, such as denial of service or block withholding attacks. Lastly, cryptocurrency exchange analysis is another task domain using external market data, but it is not the main focus of our survey because it does not include immediate blockchain data. Then we analyze how common these task domains were in our sources. Next, I will discuss each of them in more detail. The first task domain, the peer-to-peer network activity analysis, was the most common task we found in blockchain visualization tools. Typically present aggregated statistics that give an overview of activities in the peer-to-peer network, such as mining, transaction rates, and mempool statistics. As you can see from our example, most of the sources use time series chart to communicate the data. The second most common task domain was transaction detail analysis. We grouped it into three different types. First, visualization of financial transactions that allow users to search and explore transactions both on the address level, as the above figure, and for the entire blockchain, as the figure below. Second, visualization of blocks display the chain of link blocks such as the ETH viewer tool here that show real-time activity of the Ethereum blockchain. In addition, two visualization articles specifically propose visual analytics tools to explore specific group of users in the Bitcoin blockchain. BitConduit is a tool to filter groups of users visually from a classification tree on A and B panel, and then explore group of users as radar chart on C and D panel. Another tool is BitExtract that focuses on analyzing Bitcoin exchange users with a multiple link view, connecting the ranking on A, temporal activity on B and C, and connection between Bitcoin exchange on D. The third task domain, transaction network analysis, has the same number of sources as transaction detail analysis task domain. Transaction network analysis tools mainly display the connectivity of data stored in the blockchain as tree and graph visualizations. We found that visualization sources display either transaction network, address network, or user network as blockchain with tools on the left side, or trace the value flow from the seeding transaction as Henry of Cram and Bitcoin view on the right side. The fourth task domain is cybercrime detection. This task is usually overlapped with transaction network analysis, with a focus on detecting fraudulent activity and cyber attacks in the blockchain. For example, you can use transaction network tools to visualize a block and detect cyber attacks, as the example from McGinn and author's article, or use transaction value flow tools to follow thieves from the suspicious transaction. Next, the fifth task domain, casual, entertaining information communication tools target public audience and often present real-time transactions with 3D graphics. For example, Bitbonker show animated balls, Bitcoin City display transaction and block as toy model of building and road, or Bitcoin VR show a flying balloon in a 360-degree virtual reality view. The last task domain, cryptocurrency exchange analysis, display the market price of blockchain and trading volume over time. This task domain is not the focus of the survey, and we include only tools that also present data stored in the blockchain. We have a poster present at Eurovis 2019 for a more comprehensive review of this kind of tool. Okay, so far I have explained to you three classification schemes: target blockchain, blockchain data, and task domain. Now, let's move on to two other classification. Our fourth classification of blockchain visualization related to target audience. We found that the majority of visualization sources were made for blockchain user and data analyst expert. Blockchain user use the tool to monitor blockchain activities or look at the detail of blockchain components. On the other hand, data analyst expert, including investigator and economists, need tools to perform in-depth analysis of activities on the blockchain. Lastly, tools targeted to public audience usually attract the attention to blockchain technology in a casual way. Separate target audience by task domain. We observe that most casual and entertaining tools are targeted at public audience, while visualization tools for blockchain user mostly focus on the peer-to-peer network activity analysis and transaction detail analysis task domains. Interestingly, data analyst experts are highly interested in two task domains, namely transaction network analysis and cybercrime detection. These results indicate the demand for future blockchain visualization tools. Finally, looking at visualization types, time series were the main visualization type for blockchain data, followed by basic charts and tree and graph visualization. This is not surprising because blockchain data is timestamped and transaction elements are connected as a network. Other visualization types are casual, map-based, and multi-dimensional visualization. From the result of our survey, we found that the open challenge in blockchain visualization lies in three aspects. On the user side, we found a need for more specific tools for blockchain experts, such as economists, investigator, regulator, and blockchain manager, to deeply explore and monitor activities in the blockchain. Another task is to detect possible malicious user or threat to the blockchain network. On the data side, blockchain data is very large and rich in detail, so the challenge lies in processing large transactional dataset and detect users in the blockchain. In this sense, progressive visual analytics would help reduce the latency time and improve the efficiency of blockchain visualization. Finally, on the visualization side, we need visualization tools that can handle multiple levels of data aggregation and related or characteristics in a multiple link view. The future tools should allow experts to take on specific viewpoints, in particular, individual users in the network, historical event, or network-related event. Thank you for your kind attention.
Okay, thank you for this talk. Very interesting and very breadth of information. We have Natkamon Tovanich here with us, the main author. So while we're waiting for questions on the chat, oh, actually there is one. I'm sorry. So Fabian Böhm is actually asking, did you focus your survey on public blockchains?
Okay, thank you for the question. First of all, I would like to say hi to my family in Thailand watching me. Hi, Mom. Hi, Dad. I'm here. Yes, so our survey just focused on the public blockchain because we can access the visualization. And actually, because blockchain is the new emerging technology, so what we found in our survey is that we found only a public blockchain visualization that is available on both research paper, data analysis paper, and on the online tools, which I think this is an interesting field as the time goes by. We expect to see more visualization tools in other like private blockchain or consensus blockchain too.
Thank you. I was also wondering about the users that were targeted by the different papers that you surveyed. You distinguish there between experts, novices, and simply maybe just entertaining purposes. But did you also see that the papers talk about the visual literacy, the professional background of the users that were using those tools? Yeah.
Yes, it is in the blockchain user. So we classify blockchain user into three kinds. based on the expertise of people, and you can for the different kind of blockchain users, they require different level of the literacy in visualization tools. Like for example, for the public audience, they want the one that is easy to grab, maybe just a simple chart. For the intermediate, they want to see the more literate, more complicated visualization. And for the expert, they want maybe like a network visualization, or like in the previous work in this session, to look in detail and to investigate more in the blockchain, more connection in the blockchain.
Okay. Maybe one last question on. I was wondering that there was talk about that blockchains, the cryptocurrencies, they to calculate the next block is quite computing intensive, right?
Yes, right.
So from a climate perspective, was there any visualization that took up this, and how much CO2 you actually used, and in which areas? Was there something like that?
Actually, they have the research about like how much of the blockchain mining activity consume the energy, and actually there is the ongoing research in blockchain, like how to optimize this with a different policy, that maybe we don't need to run the mining all the time, but we like switch the peer to mine the block. But actually, it's very interesting. Yeah, very interesting.
Okay. Well, thank you once more. And
thank you very much.
We will continue with our next talk, which is called SilkViser, a visual explorer of blockchain-based cryptocurrency transaction data. Please roll the video.
Hi everyone, I'm Zhibin Niu from Central Southern University. This is the agenda of my presentation. The first part is background. Novel types of blockchain-based cryptocurrencies are being continuously created. Numerous cryptocurrencies developed blockchain explorers to provide online transaction data viewing services. Most exciting blockchain explorers present transaction data in textual and tabular forms. For example, here are blockchain explorers of Bitcoin, Ethereum, and Litecoin. Using textual and tabular forms has two major shortcomings. The first one is the unfriendliness for novice users. As we know, cryptocurrencies totally differ from fiat currencies. There are many special concepts and processes, such as blockchain, 6 confirmation, and coin mixing. But textual and tabular forms are not helpful for novice users to understand these concepts. The second shortcoming is the insufficient informativeness for experienced users. They want to know advanced information in daily trading. For example, clients inquire which inputs or outputs are primary in the transaction. Majors should know the recent generation trends of blocks and transactions. However, such information cannot be effectively presented in textual and tabular forms. Zhibin is a blockchain-based cryptocurrency. We participated in the revision plan of its blockchain explorer. Visualization is powerful in illustrating complex concepts and presenting advanced information. So, we propose to introduce visualization techniques into traditional blockchain explorers to overcome the two shortcomings. Let's go to the second part. Blockchain-based cryptocurrency transaction data is a multi-object, multi-attribute tabular data. It contains 4 types of objects: blockchain, block, transaction, and address. Each object has dozens of information fields and relevant concepts. We have 3 major design requirements. 1. Mainly present essential information fields. 2. Use intuitive visualizations to illustrate important concepts and processes. 3. Use appropriate visualizations to present advanced information, such as trend and distribution. The third part is visual design. We designed 4 web pages to present the 4 types of objects respectively. The 4 pages forms a hierarchical structure. This is a summary of the information for visualization in the blockchain page, including many concepts and 2 kinds of trend information. We adopt the metaphor of string of paper ledgers in the blockchain page. Long ago, people kept accounts on paper ledgers. These ledgers were strung together for easy access. The metaphor has 3 major benefits. First, a string of paper ledgers has a sense of chain. and edged paper ledgers provide a sense of history and reliability. Second, a string of paper ledgers is used for accounting, which is the same with the blockchain. At last, a paper ledger in the string can record transactions, which is the same with a block in the blockchain. So, we design a visualization to present the blockchain and blocks. A yellow square represents the block. A chain of squares represents the blockchain, which indicates the one-to-many relationship between the blockchain and the blocks. The arrow pointing to the left indicates that a block always has connected a previous block. The length of the arrow denotes the time interval for generating two blocks. When a new block is linked to the rightmost side, the leftmost square in the page is moved out, which explains that the blockchain is formed by linking continuously generated blocks. In a block, the text mainly are hash information, which indicates the blocks are connected by hash values. The statistical information includes the number of transactions, block size, and block reward. It explains that a block has a certain memory space for recording transactions. It also explains that the miners of this block can get a reward for packing new transactions into this block. Sixth confirmation is an important concept. Once a new block is created, it gains its first confirmation. When a subsequent block is linked to this block, the confirmation number of this block is added. When the confirmation number reaches 6 or more, this block and all its transactions are totally safe. We use triple visual encodes to illustrate 6 confirmation, including displaying confirmation number, using gradient colors to blocks, and only showing the latest 6 blocks. The blockchain page has 3 function areas. The top area is a query box. The middle area is the blockchain visualization. The bottom area is used for visualizing the daily generation trends of blocks and transactions in the last 3 months. This is a summary of the information for visualization in the block page. The block web page is vertically divided into 3 functional areas. The top area uses a vertical 2-column table to display the essential information of a block. The middle area is for visualization. The bottom area lists all the transactions in the block in a paging horizontal table. The square at the left represents that there are 49 transactions in this block. The circles are sum of 49 transactions. The 3 bar charts show 3 statistical distributions of transactions in this block. We adopt the metaphor of copper coins from ancient China for visualizing transactions. This metaphor has 3 advantages. First, copper coins are a kind of the financial property. Second, the bronze yellow of copper coins is compatible with aged paper yellow. Third, a copper coin has diverse structural components for visual encoding. A coin has 3 structural components: a coin wheel, a coin body, and a coin eye. The coin wheel encodes the number of input and output transactions. The color of the coin body encodes the transaction fee. The size of the coin eye encodes the transaction size. Users can sort or filter transactions by interactions to find transactions of interest. Then, users can visually compare transactions. For example, the left side transactions has more input addresses than the right side ones. This is a summary of the information for visualization in the transaction page. The transaction page also uses a 3-area layout design. The top area displays the essential information of a transaction. The middle area is for visualization. The bottom area lists all the input and output addresses in the transaction. We propose a coin Sankey diagram. The center is a copper coin glyph that represents the transaction on this page. The left circles are input addresses and the right are output addresses. Only primary inputs and outputs will be displayed. Others are merged into special circles. For example, this transaction has 16 inputs and 2 outputs. Only the top 6 inputs are shown. Most of the rubian are received by one output. A tiny part of the rubian is received by the other output. This design explains the one-to-many relationship between the transaction and addresses. This design can also explain the concept of coin mixing. That is, The inputting Zhibin from multiple input addresses is mixed by the transaction system to unlink input and output addresses. Coin mixing improves the anonymity of cryptocurrency transactions. The address page also uses a three-area layout design. The middle area visualizes the balance variant trend and the transaction participation trend of the address in the last 30 days. We provide two exploring modes. Users can select or click an object in the web page to jump to the corresponding page. For example, select a block in the blockchain page, then open the block page of this selected block. Users can also input keywords in the query bar to jump to the corresponding page. During our visual design, we produced many design alternatives. Here are some alternatives for the blockchain page. Here are some alternatives for the block page. Here are some alternatives for the transaction page. The fourth part is evaluation. Two usage cases are provided. Because of the time limit, please refer to our paper. We recruited many volunteers to conduct a user study. An objective questionnaire and a subjective questionnaire were used. We obtained lots of positive feedbacks from the volunteers. Because of the time limit, please refer to our paper. In the end, we go to discussion and conclusion. This work has some limitations. Many Chinese elements are used in SilkViser. However, we are unsure if clients from other countries will accept them. The visualizations of SilkViser has some defects. For example, the block page has a high learning cost. SilkViser cannot visualize large-scale blocks and transactions. SilkViser is currently not a visual analytics application, lacking analysis capability. In conclusion, this work presents a new online blockchain Explorer. The new Explorer adopts a series of novel visualizations to help users understand cryptocurrency transaction mechanisms and recognize advanced transaction information. That's all. Thanks for your listening.
I'm sorry. Thank you very much for this talk. We have Shuirun Wei with us. And I'm taking the first question from our chat. And here Unique Fox is asking, it is pointed out that traditional textual and tabular are not easily understandable for novice user. Why do you think so?
Thanks for your questions. Because novice users haven't experience in cryptocurrencies, so they cannot understand what is information represent. They need more visual presentation to help them understand the concept and the process. I hope this can answer this question.
Okay, thank you. Kennedy is asking, this tool does not seem to have visual analysis capability, or he actually asks, is there any plan to add more analytics or more analysis capabilities to it?
Sorry.
Do you agree? Maybe.
Yes. We have two considerations on this issue. First, a large part of cryptocurrency users have not an IT or data analysis background. Blockchain explorers have meet requirements of information in acquisition of most users. Second, a small part of users is data analysis and administrator who are interested in gaining deep insight from the data. We should provide them with other advanced visual analytic tools to dig into the data and find out complex data patterns.
Mm-hmm. Thank you. So Natkamon congratulates you to your good representation of the Bitcoin data and coin representation in your work. I agree with that. And he also asks if your tool considers comparing the data across transactions or across addresses.
For that adaptability to other cryptocurrencies. Our scenario analysis and data abstraction focus on data characteristics and user requirements common in diverse cryptocurrencies, conceptual processes, and advanced information that should be present through visualization can also be found in other cryptocurrencies. This informed ensure that SilkViser can be used to explore the other cryptocurrencies with minor modifications. And our visualization design can be shared among a variety of blockchain explorers.
Okay, this also answers my question, since I was wondering if the Silubium solution that you have right now is also applicable to Bitcoin, since it was derived from Bitcoin. But it sounds like, yes, that's relatively easy to do. I will post my questions later on in the chat, since we're also running out of time. Thank you very much for your answers and for your talk. And we will come to the final presentation for this session, and this is called AgentViz: Visual Analysis of Agent Behavior with Hierarchical Glyphs.
Hello, my name is Dylan Rees from Swansea University, and I will be presenting the work AgentViz on behalf of my co-authors. My co-author Bob Laramie will be fielding questions following the presentation. The work was carried out in collaboration with our industry partner QPC Limited, who provides technology solutions for the call center industry. This project arose from their need to visualize call center data of their clients. The datasets tend to be large, featuring millions of calls, each with multiple data attributes and many different aspects. This particular project focuses on visualizing call center agent-based data. Our design solution incorporates a scatterplot glyph-based visualization. Glyphs provide an intuitive form of conveying behavior data and were favored by our domain experts for this reason. They found glyphs to be intuitive for data analysts, managers, and for clients. Technical challenges associated with our development include designing and implementing dynamic glyph clustering criteria for different zoom levels, developing smooth transitions, and interactively rendering large numbers of glyphs. We also consider the influence of clustering behavior. We demonstrate these techniques on a bespoke application for visualizing call center agent behavior. Our application relies on a data-driven scatterplot layout. Here we have loaded a month's worth of data provided by our industry partner. This consists of nearly 5 million calls who interact with over 6,500 agents. A scatterplot matrix is available to provide an overview of all variables. A correlation coefficient is used to indicate how well correlated each plot is, and the background color of each plot reflects this, with a darker red showing stronger correlation. Clicking a plot brings that plot into the main window. Users are able to map both the X and Y axes to a number of agent properties to explore relationships between variables. Here, the user selects the total hold count for the X-axis and the average agent customer effort score for the Y-axis. The user selects the glyph option to show a multivariate glyph for each agent. A selection of glyph designs are available to choose from. The chosen glyph design has 6 bars that can be mapped to an agent property as indicated by the glyph legend. The glyph legend is also used to represent the mean of all loaded agent variables. Hovering the mouse over the center of the legend returns a dialog with explicit average values for each agent property. Clicking the center of the glyph legend returns a dialog where each of the glyph bars can be changed as the user desires. The user in this case chooses to map the percentage of calls transferred to the 2 o'clock bar and the percentage of short calls to the 10 o'clock bar. The glyphs are updated accordingly. The length and color of each bar represents the value of the particular agent variable. The color map for the bar can be seen below the glyph legend, clicking which allows for a selection of color maps. Glyph centers are color-coded to indicate the core center department of the agent. Clicking the legend allows for a choice of color mappings.
The user is also able to filter individual departments by clicking the checkbox next to the appropriate department on the legend. Hovering over an individual agent glyph returns a dialog showing property values for that agent. Users are able to use scroll bars to zoom on individual axes or by using the wheel mouse. The user is using the mouse wheel to zoom, which zooms towards the mouse pointer. The visual design suffers from overplotting, limiting the usefulness of the application. Therefore, we utilize a clustering technique to reduce clutter. By selecting this option, agents are clustered into parent glyphs according to their proximity to one another, reducing overlap and clutter. A number indicates the number of child glyphs represented by each parent, and the glyph center indicates the proportion of agents from each department. Glyph bars are updated to display the mean values for all child glyphs. Hovering over a parent glyph returns a dialog displaying the number of agents represented from each department and the mean agent variable values. As the user zooms, parent glyphs are recomputed to fully utilize screen space. As the scene is zooming in, parent glyphs are continuously being recomputed and splitting into smaller clusters and individual child glyphs. Zooming out causes the child glyphs to merge into parent glyphs. A user option allows for the filtering of all bars that represent below or above average variables. Using this view and the above average filter, we are able to see that bars on glyphs with below average Net Promoter feedback scores are removed on glyphs with high customer effort score and a large number of holds. The clustering distance metric can be adjusted to control the amount of glyphs displayed. Increasing the clustering distance decreases the number of glyphs, while decreasing the distance increases the number of glyphs. An option is also available to cluster into individual departments, skill, team, or call center site. Here we cluster agents into their call center departments. This gives the mean variable values for each department, allowing for comparisons to be made between each department. Changing the axis so that we have customer effort score on the y-axis and the average hold duration on the x-axis, we can see that 3 distinct clusters of departments can be seen. The sales and billing departments have a significantly longer hold duration in comparison to the credit, company, and collections departments, suggesting that agent resources in the sales and billing departments should be increased. The distance metric can be used in conjunction with a categorical cluster. In this case, glyphs will only cluster if they share the same department and are within the distance metric. This feature is particularly useful in finding agents that have strange behavior in comparison to others in their department. The user changes the x-axis to display the number of calls per day and the y-axis to show the percentage of short calls. In this example, we have an agent from the Customer Services Department who has less short calls in comparison to others from the department and averages more calls each day. Using the filtering option further highlights this lone agent. This lone agent among 6,500 agents deserves special recognition. Another example of behavior different from the norm is this agent from the Credit Department, with 100% of their calls being classified as short. Short calls are calls that last less than 5 seconds, too short for a meaningful interaction. By using the on-mouse over feature, we can see that only 3 calls were handled by this agent, who may warrant special attention. We further demonstrate the utility of the application with a brief case study of factors affecting customer satisfaction and how well the customer satisfaction correlates with customer effort score in different call center departments. Customer satisfaction is measured by a feedback score known as the Net Promoter Score on a scale from 1 to 10. Customer effort score is a derived multifaceted metric to determine how much effort a customer made in contacting the call center. Some of the factors that affect this are the call duration, the number of transfers, and how long a customer was on hold for. The user has selected customer feedback for the y-axis and the customer effort score for the x-axis. The main drivers of customer effort have been mapped to the glyph bars. The percentage of calls transferred is placed on the 6 o'clock bar on the glyph, with average call duration on the 12 o'clock bar and average hold duration on the 8 o'clock bar. The user filters to show only the retention department, then adjusts the x-axis accordingly. Feedback scores of -1 represent agents who have not received feedback. Therefore, they can be removed using the y-axis zoom. A negative correlation can be seen, with an increase in customer effort returning less customer satisfaction. Clustering is enabled to reduce clutter. Noticeable now is that calls with a low feedback score also have a large percentage of calls transferred, as indicated by the 6 o'clock bar. Switching the x-axis to the percentage of calls transferred and adjusting the axis accordingly confirms this. The user decides to cluster agents by their team to see what effect this has. It is noticed that the 8 o'clock bar, representing hold duration, is slightly longer on calls with a lower customer feedback, so the x-axis is changed to hold duration to study this further. Some correlation can be seen again, but noticeable again is the difference between teams with a high percentage of transfer calls and those with a low percentage of transfers, as indicated by the 6 o'clock bar. The user decides to see how the sales department compares. Immediately, a relationship between average hold duration and customer feedback is seen. Changing the x-axis to customer effort shows the same correlation. Performing similar analysis to other departments shows that feedback score correlates with effort for the tech support and billing departments. However, this is not the case with the credit, collections, and customer services departments. Development of this application was guided by our industry partners from multiple feedback sessions. The following extract comes from one of our evaluation sessions with the domain experts.
And the whole thing looks really good. Looks really good to me, really flexible. Good. It does an awful lot. Yeah. I really like it.
Thank you for watching.
Okay, thank you very much for this interesting talk and video. We have Bob Laramie here with us, one of the co-authors, and happy to answer your questions. One question that came up to my mind when I looked at this interesting design and also the glyph design was it that you talked to this application area, the domain experts, to come up with this design, or did you have the idea for the design that was most suitable for this domain?
Thank you for that great question, and thanks for letting us present. And greetings from Nottingham, by the way. Yes, so basically in the beginning, we went through a kind of exploration process of different multivariate glyph designs with the domain experts. In this case, it's the company called QPC Limited, based in Birmingham in the UK. Yes, and what we ended up doing was we basically hijacked another glyph that we used in a previous similar study on glyphs for rugby visualization. So we developed glyphs for rugby visualization with a team of rugby analysts. And that went through a very long process. And so we kind of hijacked that. And we did explore a few other glyphs, but basically what we did was we adapted the rugby glyph, which already had gone through this this long process. We introduced more glyphs to satisfy the reviewers, but in fact, the domain experts were generally happy with the so-called rugby glyphs. Yeah.
I remember those, the rugby glyphs. Right.
Thank you.
Yeah. So do you also think this might be suitable for other domains? How specific do you think it is for call centers? It's
not specific at all, actually. It's a very generic multivariate visualization framework. So it has it starts out with the scatter plot matrix overview, and then you can plot whatever you want on those glyphs, whatever attributes you want. You can choose your favorite attributes to map to the spikes on the glyphs. You can choose your favorite attributes that you map onto the axes. So it's really very generic. In fact, that was always kind of a question during the review process, is this an application paper, which we thought it was actually, but then more and more it turned into a generic technique paper as it evolved. Yeah.
Cool. Well, thank you once more, and thanks to all the authors and the questions, and thanks for having us here at VIS 2020. This was one of the last talks. Well, the only thing looking forward to now is the capstone and the closing. And this was Jörn Kohlhammer, and was happy to be the session chair here. Bye-bye.
Thank you very much.
We miss you, indeed. We miss you being in New Orleans. We also miss doing what New Orleanians so often do best, welcoming you to our city, telling you about our favorite places, and watching you truly experience the absolute beauty and indescribable magic of this incredibly special place. Everything that you know and love about New Orleans is not only here waiting for you, but it's better than ever. We have been busy getting ready for your arrival and have considered every detail of your visit with world-class dining, a brand new airport, new museums and attractions, and hotels to fit your every need and desire. Our world-class convention center is completing a beautiful new pedestrian park and is beginning renovations to other facilities. We'll even have gumbo on the stove, and our musicians are tuning their instruments. So when it comes time for you to return, we'll welcome you back to our table and celebrate with you our 300-year-old traditions. And we know that you will create new ones along the way.
Good morning, New Orleans. We love you, New Orleans.
Just know that we're thinking of you here in the Crescent City, and we can't wait to see you soon.
Love New Orleans. When people come, they never leave, because we're swinging that way. The sun shines so bright. The breeze is so nice.
Hey everyone, I'm Junqi Zhao, a PhD candidate at Purdue University, computer graphics major, and a research internship at Bosch Research North America. Here, we are presenting our recent research, Persevere, using factorized prototypes to visually interpret and diagnose deep neural network. This work is co-authored by research scientists at Bosch, Zheng Dai, Dr. Panpan Xu, and Dr. Liu Ren.
We introduce a direct volume rendering approach that can render encrypted images directly from encrypted datasets. The rendering is performed by operations in the encrypted number space, which are dual to operations in the plaintext space. Therefore, the rendering system does not need to decrypt the data. This homomorphic volume rendering approach makes it possible to use untrusted servers for rendering without compromising privacy.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. Connect to the data you care about. Sort, highlight, drill down, or filter your data in seconds. Add calculations to extend your data. With Tableau, you can keep on asking questions in the data until you discover the root cause. Tableau. Answer questions at the speed of thought.
How do user interactions lead to insights? We present a case study with a tool that supports 5 types of interactions for exploring drug-target relations. Through an evaluation, we collected interaction trails, manually extracted interaction patterns, characterized the user insights, and explored the relations between interactions and insights.
In this work, we conducted a design study with clinical researchers to develop a visual analytics application for exploring disease progression pathways. As a result, we developed VIS, which seamlessly integrates hidden markup models with interactive visualizations. The usage scenario and user experiences demonstrate the usefulness of the application to gain useful insights out of disease progression trajectories in a transparent manner.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. With Tableau, you can keep on asking questions in the data until you discover the root cause. Share your analysis securely. Your entire organization can access these interactive dashboards from any browser or mobile device to find their own answers. Tableau. Answer questions at the speed of thought.
Data stakeholders are rarely the data experts. Making tools for them means considering how they communicate about data. Rules are a convenient way for humans to express patterns in data, like we need high variable X and low variable Y. In our human-in-the-loop approach, the user selects points of interest and can immediately see rules that differentiate those data from the rest. Lots more detail in the paper, even though it's short.
We present AgentViz, an application for the visual analysis of call center agent behavior using hierarchical glyphs. Our application relies on a data-driven scatterplot layout, with each glyph representing an individual call center agent. We demonstrate the application with nearly 5 million calls who interact with over 6,500 call center agents. To reduce clutter, we present a dynamic aggregating glyph clustering technique that varies with zoom level, maximizing the screen space.
We present an interface to visually analyze and steer zero-shot learning models. Our interface is designed to diagnose attribute mispredictions to convey potential failure modes in zero-shot learning. Using our interface, the user can select multiple categories for analysis. We allow the user to steer the model by changing the weights of potentially problematic attributes based on their analysis.
We propose data-driven space filling curves. Our new method generates linearizations that better preserve coherency than existing techniques. Our method supports 3D datasets and even multi-scale data on a quad tree or an octree. Many visualizations benefit from our method. For example, visualization of multivariate particles and visualization.
Do you have a research question but aren't sure how to go about answering it? Are you interested in collaborating with psychologists but want to learn more about how they do research? Our paper presents a comprehensive toolkit of empirical methods organized across 4 categories to help you think about presenting visualizations as experimental stimuli in order to explore and measure how people perceive data. Check out our paper.
Different sampling strategies have different performances in preserving features, but which one is the best? In this paper, we selected 7 sampling strategies along with 8 representative datasets and 3 important visual factors. We formulated 4 hypotheses and conducted a user study with 100 participants. For the derived insights, please refer to our paper.
Language models are highly performant across many language understanding tasks. Comprehending the linguistic knowledge encoded by these models, however, remains a challenging problem. we introduced an approach for visually analyzing contextualized embeddings produced by language models. Our design shows how much context is captured by embeddings, the ability of embeddings to capture meaningful text spans, and linguistic relationships represented by the embeddings.
We present columnar data augmentation through visual analytics. Kava lets users augment their data with additional attributes found on knowledge graphs. To construct a new attribute, each row of a dataset is mapped to a node on a knowledge graph. Each augmented datum is the result of a query over the knowledge graph in the neighborhood of that node.
In cancer research, it's useful to group patients based on disease spread patterns to the lymph nodes. But once we create a new clustering methodology using spatial data, how do we explain spatial clustering to non-experts? In this multi-year project, we dealt with both a participatory design stage and a broader dissemination stage, and distilled specific lessons for interpreting spatial clusters.
What do you believe is the correlation between labor union participation and corporate profits of different companies? How would you update your belief after seeing this scatter plot? In this study, we use a new elicitation technique to understand how people update their beliefs about correlations after seeing different visualizations with and without uncertainty depictions.
Blockchain has gained more attention and its applications are emerging. We collect 76 blockchain visualization tools and systematically classify them into 5 aspects: target blockchain, blockchain data, target audience, task domain, and visualization type. In the end, we look at open challenge in blockchain visualization.
The mixture graph is a data structure for compressing, rendering, and querying segmented volumes. Biomedical segmentations have evolved from mere annotations to first-class modalities. The mixture graph stores the computations required to render such nominal data directly on the GPU, including pre-filtering and lighting. Segment distributions can be queried efficiently using regions of interest.
TaxThemis is an interactive visual analytics system to help tax officers identify suspicious tax evasion groups. The system integrates the traditional data mining algorithm and visual analytics techniques. 4 coordinate views are provided to support interactive exploration of tax evasion evidence. We demonstrate its usefulness through case studies using real-world test data and expert interviews.
We miss you. Indeed. We miss you being in New Orleans. We also miss doing what New Orleanians so often do best: welcoming you to our city, telling you about our favorite places, and watching you truly experience the absolute beauty and indescribable magic of this incredibly special place. Everything that you know and love about New Orleans is not only here waiting for you, but it's better than ever. We have been busy getting ready for your arrival and have considered every detail of your visit with world-class dining, a brand new airport, new museums and attractions, and hotels to fit your every need and desire. Our world-class convention center is completing a beautiful new pedestrian park and is beginning renovations to other facilities. We'll even have gumbo on the stove, and our musicians are tuning their instruments. So when it comes time for you to return, we'll welcome you back to our table and celebrate with you our 300-year-old traditions. And we know that you will create new ones along the way.
Good morning, New Orleans. We love you, New Orleans.
Just know that we're thinking of you here in the Crescent City, and we can't wait to see you soon.
Love New Orleans. When people come, they never leave because we're swinging that way. The sun shines so bright. The breeze is so nice.
Traditional flow visualization methods, such as the line integral convolution, convey information about its underlying flow structure. However, the influence of regions in the flow on each other is not visualized. In my talk, I will present a new dense flow visualization technique, creating a multi-level hierarchy that provides insight into the region's connectivity using a probabilistic model. For more specific details, come to my talk.
We present a high-quality tube rendering method for 3D line datasets. GPU-based raycasting is used to render line segments as rounded cones, to allow for smooth connections along individual lines and variation in radius. We support transparency by a novel approach combining visibility order rendering with an order-independent transparency method. To improve depth and feature perception, ambient occlusion is employed.
Visualizing the performance progression of machine learning techniques is often achieved by plotting the accuracy in a line chart. For specific tasks such as multi-class classification, they hide important factors such as inter-class confusion and instance-level details. We propose Instance Flow, a tool for interactive visualization of the evolution of classifier confusion on the instance level.
The transmission of pathogens such as bacteria and viruses is an acute problem in hospitals around the world. Infection control experts need to monitor infections and determine transmission pathways. We developed a novel visual analytics system for the exploration of disease outbreaks. It combines several interactive views and a tracing interaction that allows to detect pathogen transmissions.
It is common for users to struggle to understand how to effectively use TSNE. No idea how to select hyperparameters, assess the quality of the results, investigate the existence of shapes and other patterns. TVSNE covers all these tasks. We provide diverse projections to choose from, global and local quality assessment, investigations of shapes and patterns, and more.
Traditional clustering tools do not include users in the analysis loop. We present PK clustering, a new approach for interactive clustering using VIS. First, users specify their prior knowledge. Several algorithms are run and match with the prior knowledge. Users then build a consolidated clustering iteratively with suggestions based on consensus, the graph, and their knowledge of the data. The result is a consolidated clustering.
Exploring the emotions of students in classroom videos can help both teachers and parents know about students' learning status and further help teachers improve teaching. However, it is a non-trivial task to analyze the emotion evolution of a group of people from classroom videos due to three major challenges. We propose a visualization system which integrates the model uncertainty and supports both collective and individual emotion analysis.
VIS has been successfully helping not only experts but also people who want to learn about AI. At VAS 2018, we presented GANLab, an interactive tool for learning about a deep learning model called GAN. But how does VIS help these learners? We conducted 2 evaluation studies, including log analysis of our demo used by over 100,000 people. We will be sharing our findings with you.
We present our work on data visualization, a technique which helps facilitate understanding of physical measurements and quantities by providing visible experiences to users in virtual reality. This allows them to experience the ground truth of what the data is in reality, as compared to the abstract nature of conventional data visualization. We hope our work will spur new considerations into how immersive technologies can be used for visualizing information, and that you will find it interesting.
To interactively explore and visually analyze large multivariate data. For example, this cosmological simulation that is clustered into dark matter halos. We create a probabilistic data model in each cluster. We present a complete visual analysis system based on this data representation, which is especially well suited for the density-based visualizations shown here.
Nowadays, data is often distributed and owned by different participants. There is an emerging need to provide a joint visualization, such as a TSNE projection, to serve as the full picture in data analysis. If the participants are privacy sensitive, How can we build a joint projection without data leakage? Conventional embedding algorithms, such as the TSNE, are designed for single-site computation and require data centralization. Privacy leakage may happen in 3 stages in the visualization pipeline.
Firstly, we extract contours of virions and distribution of spike proteins. From a newly estimated contour, a 3D mesh with evaluated triangles is obtained. In the last step, rules describing relations between protein instances are defined by the user. The resulting model is created by application of all rules on the generated 3D mesh.
Visualizations are about visual patterns. But there's more, much more. We show the connections between more than 100 arguments on why visualization works. And don't forget to check out our website.